Welcome to the explainer. You ever look at something and wonder, hey, is that a real pattern or is it just a random coincidence? Well, today we are diving into the statistical tool that helps us tell the difference. It's all about separating a meaningful trend from just random noise. Let's get into it. All right, to get us started, let's look at this question from a Harris poll back in 2012. They went out and asked a bunch of people straight up, do you think Wall Street folks are as honest and moral as everybody else? Now, what do you think people said? The answer is pretty telling. Whoa, look at that. A huge majority, 68% said no. Now, your gut feeling is probably screaming, that's a big deal, right? But here's the thing with data. A gut feeling isn't enough. We need a way to know for sure if a result that's skewed is a genuine signal or if it's just statistical noise. And that is exactly where the tool we're talking about today comes in. And this really gets us to the heart of the matter. It all comes down to a fundamental conflict, the difference between what we actually see in the world versus what we thought we were going to see. First up, we have what's called observed frequencies. And you know what? It's exactly what it sounds like. This is the real world stuff. It's what you actually go out and count. It's your hard data, your evidence. It's the 68% of people who said disagree in that poll. It's reality. Now, on the other side of the coin, we have expected frequencies. This is our baseline. It's what we would predict we'd see if our starting theory was true. Statisticians have a fancy name for this, the null hypothesis, which is just a formal way of saying, let's assume nothing special is going on here. For example, we might expect opinions to be split 50-50 or for customers to be spread out evenly through the week. And this is where our hero, the chi-square test, enters the picture. Its one and only job is to measure the size of that gap, the gap between what we observed and what we expected. It crunches the numbers and spits out a single value, let's call it a gap score, that tells us just how far apart reality is from our theory. A bigger score? That means a bigger gap. So how do we actually put this thing to work? Well, the first big application is something called the goodness of fit test. It asks a really simple but powerful question. Does the data we collected actually fit the theory we started with? Let's make this real. Imagine you're a bank manager and you've got a simple theory. People use the ATM pretty much the same amount every weekday. But is that actually true? You're not going to just guess. You're going to collect the data to see if reality fits your even-Steven theory. And to figure this out, we follow a simple 5-step game plan. First, you state your starting assumption, that ATM use is equal. Second, you choose your weapon, the chi-square test. Third, and this is important, you set the bar. You decide ahead of time what counts as a big enough gap. Fourth, you do the math and calculate your actual gap score. And finally, step 5, you compare your score to the bar you set and you make the call. Okay, so this table lays out the battle perfectly. On one side, you have the observed column. These are the real numbers of people at the ATM each day. And on the other, the expected column. That's our no pattern theory, just the weekly total divided by 5. And you can already see it, can't you? There's a pretty big mismatch, especially on Thursday and Friday. So we run the numbers through our chi-square formula, and boom, we get our single gap score, 23.184. This one number sums up the entire difference between reality and our theory. But is it big enough? Remember that bar we set earlier? And the verdict is in. Our score of 23.184 is way, way bigger than the bar we set for ourselves, which was 13.277. So what does that mean? It means the gap between what's really happening and our theory is just too big to be a random fluke. We have to reject our initial assumption. ATM usage is definitely not the same every day. All right, so that's one use. Now for the second major way we use this tool, the test of independence. This one helps us answer a totally different but equally important question. Are two different things related to each other, or are they totally separate? Let's use a more modern example. A researcher is curious. Is there any connection between a person's gender and whether or not they own a smartphone? Or are those two things completely independent? In other words, if I know your gender, does that give me any clue at all about whether you own a smartphone? So look at this table. It's the same idea. Observed is the real data from the survey. Expected is what the numbers would have to look like if there were absolutely zero connection between gender and owning a smartphone. And once again, you can see a gap between what we're actually seeing and our no relationship theory. So we calculate the chi-square score for this gap, and we get another powerful number, 21.445. This quantifies the total difference between the real world and a world where these two things have nothing to do with each other. And the result? It's decisive. Our score of 21.445 completely blows past the critical value of 3.841. The gap between reality and our no relationship theory is way too big to be a coincidence. So we have to conclude that, based on this data, yes, gender and smartphone ownership are related. So we've seen two powerful tests that use the exact same core idea. Let's just take a second to nail down the key difference between them. Think of it like this. The goodness of fit test looks at one thing, like ATM usage, and asks if it fits a specific pattern. The test of independence looks at two things, like gender and smartphones, and asks if they're connected to each other at all. So one group, one pattern, versus one group, two variables. Simple as that. Okay, so beyond a stats class, why does any of this really matter? Well, it matters because this amazing little tool gives us a reliable, structured way to make decisions based on actual evidence instead of just a hunch. In the end, the power of chi-square is that it takes a vague feeling, like, Friday sure seems busier at the ATM, and turns it into a cold, hard number. It gives us a way to scientifically test claims, to uncover hidden relationships in our data, and most importantly, it gives us a framework to move beyond just our gut feelings. It's how we let the data do the talking. So the next time you see a statistic, or you notice a trend out in the world, you can ask yourself that question. Is what I'm observing really all that different from what I would expect by pure chance? Now that you know how to spot a real pattern, what will you question next?